For today and tomorrow and the next day, we are going to use some videos to help us understand and visualize what is happening on Earth to explain what the graph shows and how this relates to seasons and Earth's place in space. In order to do that, you will need 2 sticky notes for today. And we are going to begin by watching a video that you watched Friday. Yeah, sure. The last time you did science, you were supposed to watch this video. Today I'm going to talk you through it, and we're going to add some sticky notes to the graph where the video explains what we see in the graph. So when you have your supplies gathered, go ahead and watch the rest of this.
Science! Welcome to the Science Asylum. I am Nick Lucid.
Yeah, I know, I'm playing him again, but he went to the trouble of making this video, so he deserves to be able to get the credit for it.
Different depending on where you live. There isn't a whole lot of variation in temperature in the tropics. It's warm sometimes and hot other times. It never really gets cold. It makes more sense to discuss a dry season and a rainy season. The Arctic areas are mostly just cold all the time. Parts can even go months straight without any sunlight. In the temperate areas, though, you basically have 4 seasons. Spring, summer, fall, and winter. Plants bloom in the spring, it gets hot in the summer, trees lose their leaves in the fall, and it gets cold in the winter. But why? Why does this happen? Oh, it's because Earth is closer to the sun in the summer, right? Oh, no.
Hopefully you caught that last time. Summer does not happen because Earth is closer to the sun.
No. Actually, here at 42 degrees north latitude, we're further away from the sun in the summer. 3.3% further away. Wrap your mind around that. So why is it so much colder in the winter? Because the Earth is tilted. It does.
Now, one thing to think about, he is talking from Detroit. Our data here in this graph comes from Alaska, way up here. So our data is going to be more extreme than what he shows.
Doesn't really matter how far away the tilt has moved us from the sun either. Again, at 42 degrees north latitude, I'm only tilted about 2,100 miles further away from the sun in the winter. That might seem like a lot, but the Earth is 93 million miles from the sun, so 2,100 miles is only about 2/1000%, which is much less than the 3.3% we get from orbiting the sun. And we already said that didn't matter. What the tilt of the Earth does is it changes the angle at which light hits the ground.
So this begins to be important. I will include this in the sticky note that I show you in a moment that I will expect you to copy.
There's a shallower angle in the winter, so the light is just sort of grazing the ground. In the summer, though, the angle is steeper, causing the light to hit the ground more directly. What does that have to do with anything? Doesn't the Earth get the same amount of light regardless? That's actually a really good question. The energy you get from the sun is not the same as the energy the Earth gets from the sun. Energy is something you receive as an amount, kind of like money. First, you want to know how often you're getting it. Knowing you're getting $1,000 isn't very useful. Is it 1,000 per year? 1,000 per month? 1,000 per week? 1,000 per second? 1,000 per second would be pretty awesome, actually. It matters. When it comes to energy, we usually measure it per second, which is where the watt comes from. It also matters how it's being distributed. Is it just you receiving $1 per second, or your entire town? If it's your entire town, then you are probably receiving less than a penny. When it comes to energy, we usually measure per square meter. If we consider both of these things, then we'll be measuring joules per second per square meter, or watts per square meter. This is what we call intensity. Ignoring complicated things like clouds and other weather patterns, if the Earth were flat and facing the sun, there would be 1,365 watts per square meter hitting the surface of the Earth.
Where would Alaska be? Alaska would be up here. Since the tilt goes in this direction, this would be showing you winter in Alaska. It's summer down here because the sun is over here, and so this is the part that is tilted toward the sun.
The Earth. Slap a simple atmosphere in there, and that goes down to about 1,000 watts per square meter, because the atmosphere absorbs some of the light on its way in. Fortunately, the Earth isn't flat. On the winter solstice, you are tilted as far away from the sun as possible, which means
So remember, Alaska is up here. So in the winter, it's tilted as far away from the sun as possible. Where is this on our graph? Well, as far as possible will either mean here or here. Those are the extremes. You can figure that out in a couple of ways. You can look at the months and decide when that would be winter. You could look at the amounts of daylight. Do I expect winter to have the least daylight or the most daylight?
The light is spread out over the widest area. Less energy per square meter means the intensity is lower. On the summer solstice, you're tilted as far toward the sun as you ever will be. So the sunlight you're getting is more direct. More energy per square meter means the intensity is higher. This graph is which means the light is spread out
right about
1,000 watts per square meter because as possible, which means the light is spread out over the widest area. Less energy per square meter means the intensity is lower.
There is where I want it to pause, because we are going to label this graph now with some details about summer. And you'll notice I didn't use the whole sticky note, so I had it pre-cut, so it's ready to come off. My summer is right up here. Some information that I got from this video about summer that helps explain this graph. The north is tilted toward the sun. This is when I have the most sunlight hours and the most direct sun energy. So technically I could put this as much to the June data point as possible. It would also be true here and here and here, because all of those are June. What should I say about the winter? Well, the north would be tilted in the winter away from the sun. In the summer, it was over here. In the winter, it's tilted in this direction. What about how many sun hours? Summer had the most sun hours. Winter should be the opposite. It should have the least sun hours. And as you look at this, you should see we have very indirect sunlight. It's almost like these could just bounce right off and go back out into space. So our winter hours, trying to figure out how to cover up the least possible. This works right about here. In winter, the north is tilted away from the sun. It has the least sun hour, least direct sun energy. Now, I'm not going to have you watch this entire explanation here. Remember, this graph is showing you the intensity. But you should notice some similarities, right? In the winter, is it the most intense or the least intense light? It's the least intense. It's just a little over 400. So we have the least direct. I could have said the least intense sun energy in the winter. In June, we are the highest up on the up and down axis is always the y-axis. So this is the largest amount on the y-axis. This is the largest amount of intensity. So summer has the most intense light. That matches this. Fall and spring equinoxes, they are pretty equal. So I could have marked those as well on this graph, but all I want you to have today are these two sticky notes added to your graph explaining how this data is beginning to show us more about the seasons on Earth.